simulations. Okay. So the homeworks in this course have a point, and the point of this second homework, here are the points. First of all, optimization with more assets. So instead of 4 assets, 10 assets, just to show you that this is doable. Excel actually, as far as I can tell, has no problem doing several hundred assets. But then you get a problem that you can't really see what you're doing. So problem 1 is not a big deal. Problem 2 is actually the important problem here. And the point there is that optimization with historical data produces weird portfolios. So the particular point in problem 2 is this data set that I gave you of 10 arbitrary assets doesn't have a single all positive portfolio on the frontier. Now for the capital asset pricing model, for example, that's a big problem because the capital asset pricing model, it says that the market portfolio should be on the frontier, and the market portfolio is a portfolio of all the assets at their market weights. So it's by definition positive. And then there's some stuff that I'm not going to go into today, which I think is pretty obvious about computing the global minimum variance portfolio and doing some shrinkage calculations. Okay, so let's do the homework. And then Black-Litterman, which is the point of the first part of this, this talk, this lecture, is a way of getting away from weird portfolios. That's the way I like to think about it. All right. So here's the homework, and the first question was, if I take this variance-covariance matrix and these historical returns, can I compute the efficient frontier, and what does it look like? And I will find the answer, which I will send you tomorrow morning. Okay, so we already know the answer to this question. The answer to this question is you take 2 constants and you find the efficient portfolios for these 2 constants. And let me just remind you that this technique I showed you last week, right? I had fact 1 or proposition 1, which was that an envelope portfolio is S inverse expected returns minus C divided by the sum of the numerator. That's just a technique for finding this portfolio. So you start from C. So C looks like a risk-free rate. You start from C. You do some optimization. You come up with this condition. This condition, in fact, doesn't define a maximal portfolio. It just defines an envelope portfolio, which in mathematical terms is like saying that I looked at the first derivative, I didn't look at the second derivative. So it's possible that you take a very high C and you get some suboptimal portfolio. All right? So we've done this now several times. Here in this particular exercise, I took, let's say, 5% and 0%, and I found 2 portfolios. Then I did a sample portfolio computation. That's the one down here. And then I did a data table, and I graphed the mean and the variance, sorry, the sigma and the mean, And here's the graph, and you can play around with that. It always gives me great pleasure to see that from an arbitrary data set, you get this kind of curvature. So that was the first question. Now, the second question is, what are these portfolios, and can you say something about the positivity of these portfolios? So, for example, if I look at this portfolio, I see that there are several negative entries. And if I look at this portfolio, I see that there are also several negative entries. They switch. Okay? In fact, they switch in ways that are actually sort of surprising, because look at the data. All right? Try to think about this logically. So I have, this data set I have has several terrible assets, but it has one wholly idiotic, insane asset, right? YCRW, this trucking company, which I'm proud to say I own several hundred shares. They're not worth anything, so it's not a big investment. And this trucking company over the last 5 years has lost 11% per month. That means basically it's gone from $50 a share to zero. You know, every month you lose 11%. It adds up. Okay, so if that's your prediction of future anticipated returns, what would you say about this? Well, you would say, you know, short this thing like mad. The interesting thing is that it's not always true. I mean, when the interest rate is 5%, then actually YCRW doesn't come up negatively. Now, is there an answer to that? Did I do something wrong here?
Maybe it's just minimizing the
maybe it has to do with this effect, because 5% is itself, I'm not supposed to point at this board, 5% itself is a very weird number because this is monthly data. So 5% is, you know, sort of 60% per year. All right, so the chances are that this 5% portfolio is itself suboptimal. I suspect that that's true. But I can tell you that even for standard data, sort of more normal in the sort of more regular returns, sometimes you find strange things that happen. And one of the reasons strange things happen is because of the covariances. Okay, one of the messages of the capital asset pricing model is it's not just about variance. It's not just about returns. It's also about covariance. So you can have a lousy asset that you might want to include in your portfolio because it has negative covariance with other assets. So I don't quite know what's going on. Okay, so here's what I'm going to do. I'm going to tick these portfolios, and I want to check if there's an all-positive portfolio. Now, I have 3 methods that I can propose to you. I'm only going to show you one method analytically. Okay? Here's the first method. The first method turns up in one of my slides. The first method is you take a lot of constants C. And what?
Method for what?
The method to see if there is an all-positive portfolio. I think I did this in class, actually. You take a lot of constants, and you build a big table, and the table looks like this. Here is C, and here is the portfolio. All right, so for every C, you have a portfolio, and then you do a little check, and you see what's the minimum XI in the portfolio. So you look at this list, and you say, well, do I have, right? What does it mean to have an all-positive portfolio? It means that the smallest X, the smallest asset proportion is positive. Okay.
Instead of portfolio, I have to
the individual assets, right, so it's portfolio, it's X1, X2, okay? And then you sort of make up a story and you say, well, if for a lot of C's there are no positive portfolios, then also for the distance between these two C's there are no positive portfolios. That's okay. I'll accept that as an answer. Okay? Here's another answer you could do.
Wouldn't the interval here make a difference?
Yeah, the interval makes a difference, but let's say you make small intervals.
How small?
I don't know, 0.1%.
Yeah.
Okay? And then you see what happens. Yeah. If you don't like that, make 0.01%.
It's always the question. Did you take a...
Yeah, did you take a small enough interval? That's okay. Okay, the second method would be you take solver. Okay? And now I'm also going to take solver. That's my method. But in this method, you take solver and you solve for all positive portfolios. Solver lets you put in conditions on the maximization. No. There's a chapter in the book. It does it. There's a little macro that runs things. I'll let you do this yourself. Okay? Now, so you could take solver and you could solve for an all positive portfolio. Now let's think for a second about the relationship between an all positive portfolio and a portfolio which is optimized without constraints. What's the relationship? Where is the frontier? Lower. Actually, it's not just lower. It should be inside, right? Something like this. I don't know. Okay? So, if it's completely inside, then, right, if this frontier, this is the no short sales, and this is the short sales allowed portfolio. If it's like this, then you know that there's no all positive portfolio. Okay? Maybe it's not like this. Maybe, do I have another color here? Maybe it goes like this. It can't go above. That's a but maybe over here there's a portfolio which is, on both things, on both frontiers. And that's the case, then there is a frontier portfolio which is all positive.
What is this going to be the shape?
What?
What is this going to look like this when it's a short sales allowed and not allowed?
What?
Why is it going to look like this?
Why?
Yeah.
Because when you change the question is, why is the no short sales portfolio inside the short sales portfolio? Because you've restricted it. You've allowed less degrees of freedom.
It's usually you should say when you are above on the right corner. Like
No. This is not the usual short sale problem. This is the problem where I say, give me the maximum return I can get when I don't allow any negative proportions. So that's got to be less in principle than the maximum return I can get if I do allow. If I do allow, I also allow positive, right? Okay, so that's second. That's two methods. Yes?
That doesn't prove anything.
Should prove something if they...
It proves that solver couldn't find it.
No, you know what? First of all, let's assume that solver is this amazing program which knows everything. But second of all, when you do numerical analysis, usually the answer is that you have to know part of the answer before you can actually understand what the answer actually is. So suppose I did solver with no short sales and I got a point like this. Okay, that's no big deal. Then I go and I look on the blue line, and I see if I can find that point, and then I've solved it. You see what I'm saying? Don't worry. It works. Okay, here's what I'm doing in this spreadsheet that I'm going to send you tomorrow morning. What I'm going to do to answer this question here is I'm going to look, so this is method 3. I'm first going to look at the minimum proportion in the portfolio. So I'm going to say, given C, what's the minimum xi? So here's an example. Here's C. Right now it's 5%. Let's say it's 2%. Okay? When the interest rate is 2% per month, the minimum proportion in the portfolio is minus 0.21. Okay? And now I'm going to take solver, and I'm going to say, I'm going to go to solver, and I'm going to ask a question. What is C so that the minimum, that's this thing, is maximized? And then I'll see what it is. Here's how I do this. I love solver. One of the reasons is that once you put solver in your spreadsheet, it stays there. So I already did this. So I say data, solver, and here's the sheet. The sheet says, the solver sheet says, what's the objective function? Here it's B45, which is this function. Set that function to a maximum. So take the maximum of the minimum. And how do you find that? By changing B15, and B15 is this thing up here. It's the proportion. It's the constant. Okay? And then you have to say a little prayer. And solver keeps getting more, it keeps getting more complicated and more efficient. So in the old solver, you just hit enter. Now they've got all kinds of different solving methods. Okay? But here I'm just going to take whatever they offer me, and I hit solve. And it says, you want to keep this, or you want to restore the original values, and I say yes. So here's the answer. The answer is when the interest rate is 5.266% per month, or the C is 5.266%, then the proportion is minus 0.4. So that says that even if you maximize the minimum proportion, it's still negative. It all, you see, I have this blind faith in solver. It all depends on the assumption that solver actually knows what the hell it's doing. Okay? But if this is true, then on the whole frontier, there is no all positive portfolio. Okay? I can tell you, what? I take the minimum, and then I say make this minimum as large as possible. So as little negative as possible, if you like to think about it this way. So if I get a positive number, then there's an answer. What?
If it's larger than it's not.
If it's larger than 0, it's the minimum, then all the ones above it are also larger than that, and so I have an all positive portfolio.
Least negative. You said as negative as I can.
This is what, it's not the least negative, it's the most positive negative. Okay, so that's the method. I can tell you that I've been teaching this particular version of this course for about 5 or 6 years. Okay, I've done this problem with every year I do the same thing. I pick 10 stocks that I happen to remember their stock symbols, and I do 60 months of data, and I always get the same result. So I'm willing, this is not a mathematical theorem, but I'm willing to propose a common sense theorem that says that no matter what data you take, you will never get an all-positive portfolio on the frontier. It's a little risky, but okay. So that's the homework. The rest of the stuff is too simple. I'll just send it to you. All right. So how does this connect? How does this connect to the Black-Litterman model? So now we get to the main point of this particular class, which is this particular model by Black and Litterman. This is chapter 13 of this book. I'm not going to do the whole model today because it's too complicated. I want to make sure that you understand the basic point of the model. And then next week we'll do one other little thing. Okay, so Black is Fisher-Black, the same. So this is sort of my Fisher-Black memorial lecture. The first half of the course, the first half of the lecture, I do the Black-Litterman model, and the second half of the lecture or the class, I do the Black-Scholes model. The same Black, quite a guy, and Mr. Litterman, who was at Goldman Sachs, or was. Okay, so this is a lecture I've given in many places, so forgive some of the repeats that we've done before. Just to remind you, what's a feasible portfolio, what's the envelope, all of that stuff. Okay, here's a version of that first proposition by Merton. I just wrote it out with words, okay? So what's written up there is it says that an envelope portfolio is S inverse ER minus C divided by a constant. Now, instead of saying the sum of the numerator, which is what I said before, let me write a general Greek letter and say lambda. So lambda is a normalization factor. So we've already seen that. You know what it means. Okay. Now I want to tell you what I call 4 stylized facts about portfolios. You know what a stylized fact is? A stylized fact is sort of bullshit that's true. I went to Wikipedia, which is one of my favorite sources these days for everything. Because if I don't like what's written there, I could write my own entry and just say, you see, it says so in Wikipedia. No, I didn't write this. The Wikipedia entry for stylized fact says, in social sciences, especially economics, a stylized fact is a simplified presentation of an empirical finding. And then it gives some examples. So here's an example. Every level of higher education, high school, college, diploma, blah, blah, significantly raises lifetime income. Okay? It's actually not totally true. You know, you can, as the next paragraph says, you can find people who have PhDs that reduces your income. Not in my case, let me say. I'm a very happy person with my PhD. But, you know, a stylized fact is just sort of one of these things that people say that is more or less true. Okay? So I'm going to give you 4 or less, more or less true facts about portfolios. And this is the basis for Black-Scholes. And I'm going to devote a few slides to each one of these facts. So here's the first fact. The first fact says that a benchmark is generally ex post inefficient. Now, let me explain to you what I mean by a benchmark. When I say benchmark, wrong color. What I mean for purposes of this discussion is a portfolio which could be some kind of a standard. I'm going to have very, very simple examples because I like these 3 or 4 asset examples, and I'll call those benchmarks. But benchmark, think about it, things like the S&P 500 or the Tel Aviv Stock Exchange 25 or the stocks 50, or you can make up your own, you know, the DAC. How many in the DAC these days? I have no idea. The Financial Times 100. You know, one of these indices, think about it that way. Okay, so the first fact says, I'm going to go over them, right? Benchmarks are generally ex post inefficient. The second fact says it's hard to beat benchmarks. The third fact says that optimized portfolios contain strange positions. That actually I've already talked about. Okay, so that fact just says you take some data, you do optimization, portfolio optimization, chances are you won't like what you see. And the final fact is that the historical data is a bad predictor of future data. Okay, so let me give you some examples. All right, so here's the first. I'm going to repeat them all. Okay, so here's the first example. Benchmarks are generally ex post inefficient. All right, so here's a paper written by a guy named Tal Schwartz. And Tal Schwartz, for years I used this example, and I used to walk around saying, Tal Schwartz, who the hell is that? He must be an Israeli, right? And because I just read the paper on the web. And then one day I got a telephone call from somebody at the Technion, and he said, hi, my name is Tal Schwartz. I said, I've been looking for you. I couldn't find him. Okay, so Tal Schwartz was an Israeli doctoral student at Cornell, and he wrote a paper, and here's what he did. He took data for the S&P 500, and he computed the efficient frontier. This 1, 2, 3, 4, 5, those are just portfolios on the efficient frontier. Okay? And as a small criticism, we're now friends. So as a small criticism, let me say that if he had read Merton's paper or my book, then he would have had a better way to do this, right? You see from the way he did this, he did it piecewise linear. So he took a lot of portfolios, and then he optimized, and then he connected them with little lines, okay? But if he'd computed the covariance matrix, it's only 500 assets, he only would have had to compute 2 portfolios. Okay, never mind. Here's the efficient frontier. And then he said, where is the S&P 500? And the answer is, the S&P 500 is inside the efficient frontier. Okay, so what does that prove? Well, that proves that you could improve your performance over the S&P 500. For example, you could go from the S&P 500 this direction, and portfolio 5 would give you the same standard deviation but better returns. Or you could go this direction, and portfolio 2 would give you the same expected return and less standard deviation. Okay? There used to be a whole investment industry based on this kind of logic. There was a company whose name I can't mention because I'm being taped. formed by two famous finance professors, and their pitch was exactly this pitch, which is, you give me a benchmark, and I'll show you that I can outperform the benchmark. I can outperform it. I can show you how to get, in this quadrant, my mouse doesn't work here, like this quadrant. Okay. I don't know. They made a lot of money, but nobody uses that method anymore. Okay, here's another example of ex post inefficient. When I say ex post, what do I mean? What does that mean? Ex post versus what? Yeah, it means if you took the historical data in hindsight, you could have done better.
Okay, that's true about everything.
Well, it's true about almost everything. Right. Yes. As the Hebrew saying goes, if my grandmother had had roller skates, I would have been a bus, or something like that. I don't know. Something. Okay, so here's another example. The premier bond index used to be the Lehman Brothers index. It's now the Lehman index. It's now the Barclays index. This is this index of most commercially available bonds, corporate bonds in the United States. Okay, so here's something I found on the web. This is already quite old. Here's a company. They have their own indices off it. And the purpose of this curve is to show you that here's the Lehman index, but if you'd combine that index with the Offutt indices, then you would have done better. So that proves that the Lehman is ex post inefficient. Okay, you can make up your own examples like this. As I said before, it's not hard. Just take some data. I promise you, you'll find a drawing like this or like this. Okay, here's the second thing, and that's the thing that we're supposed to have already taught you in an investments course. The second fact is it's very hard to beat benchmarks. In fact, it's almost impossible. I'll just give you, again, not very up-to-date stuff. Okay, so here is a survey by Lipper Analytical Services that says in a particular period, 80% of all general equity funds underperformed the S&P 500. And, you know, here's some more things. It says that most actively managed stock funds underperform the indices, the S&P or whatever the relevant index is, by about 1.8% per year. There's some questions there. I hope you've talked about this in an investments course. Anybody have any comments on this? One comment you could have is, I'll get back to these slides in just a second. Here's an article by John Bogle, the man who really started index investing in the United States. And the point of this slide is, there are 2 points of this slide. One is that costs are very important. So an average mutual fund in the United States has a cost of about 0.8%. So even if they knew what they were doing, and even if they were amazing stock pickers, then they would start off with a disadvantage of about 0.8% or 1% per year. That's a big disadvantage in a stock market. The point of this slide actually is that, I'm not going to go through the numbers, but that if you look at funds, then the performance of funds is negatively correlated with the size of their expense ratios. So you might expect, if the world were, if people knew what they were doing, I'm sure somebody in here manages funds, and I'm sure you're better than this, but if fund managers knew how to manage funds, then you would expect that people would be willing to pay for the management, and therefore better performing funds would have higher expense ratios because you get better management. But in fact, ex post, it turns out to be the other way around. Okay. Here's another fact about it's hard to beat the indices. Okay, so this is a study by two researchers at Duke University, and they looked at investment newsletters. Investment newsletters are, you can buy them, you pay some money, and you get some advice. And these two guys, Graham and Harvey, they tracked what you would have gotten if you had invested in the advice of 257 investment newsletters. So every month you get the newsletter, and you go out and you buy whatever it is, the portfolio that they recommend. And then, instead of just comparing performance, they compare the performance relative to the standard deviation. Okay? And what you see here is that most of the performance is underneath a line that tracks it's underneath the capital market line, if you want to know what it is. Okay? That red line is the capital market line. So again, it says, you know, if you want to beat the index by following advice, paying for advice, then most of the time you're not going to succeed, even though, look, here's somebody who really knew what they were doing, right? You bought this newsletter and you outperformed the S&P 500. There's another great study by a guy named Malkiel who is at Princeton University. This is actually a paper in the Journal of Finance, and Malkiel looks not only at portfolio alphas. Here's the graph of portfolio alphas. What's the point of this graph? Anybody see? It's normal, but what do you say about the average? It's slightly left skewed. Okay? Why is that? Well, no, you have to pay a fee to invest in a mutual fund. So, you know, what you would expect is, without the fee, you would expect the alphas to be normal, but with the fee, you expect the alphas to be, unless you're buying performance. If you're buying performance, then you outperform the fee. The other thing that Malkiel does that I don't show you here is, this refers actually to this portfolio up here. Okay? The question is not just do people give good advice, but the question is, if you give good advice this month, are you also giving good advice next month? Okay? So if you ever want to read a very, very well-written paper, this paper by Malkiel, and what he does is he tracks and he sees if funds that outperformed in one year also outperform in the successive year. What do you think the answer is? Well, the answer is actually very interesting. The answer is 40 years ago, the answer was yes. 40 years ago, it appears that markets were, this is my interpretation now, markets were inefficient enough so that you could actually use knowledge and produce superior returns. So there were some fund managers who were better than other fund managers. And that was sort of consistent. Okay? In the last part of this study, and it ended in 1995, in the last part of this study, the answer is no. There's no consistency. Funds that outperformed one year didn't outperform the other year. Okay, so it's hard to outperform indices. Here's just a cartoon. You're supposed to put cartoons in your PowerPoints, right? So, okay. Here's another thing that we've already done, although I'll show you a local example. All right. I used to have an exercise in this course where I took the Tel Aviv Stock Exchange data. The Tel Aviv Stock Exchange produces data for 8 baskets. So they have a basket for financial companies and for production companies and for, I don't know, tech companies, okay? And I used to take 60 months of data, and I would say to students, optimize, and they optimized. And then I would say to them, what's the largest short position in each of these portfolios? Okay, and the answer is that the largest short positions are truly spectacular. 50%, you know, down here 100%. So, you know, what's the point? The point is every single portfolio on this frontier contains negative positions. And the negative positions are very large in some cases. So this is, what does it mean 50%? 50% means the following, negative 50%. It means somebody comes into your office and says, I've got $100,000 or shekels. What do you advise me to do? And you say, you know what? I think you should start off by borrowing another 50,000 shekels. And then we'll do an optimal portfolio. Okay? And you say, how do you borrow? And you say, well, take this particular index or stock and short sell $50,000 worth of it, or 50,000 shekels. Okay? It's the kind of advice. I know what the client does in that case. What the client does is he says, you know what? Thank you very much for the coffee. Let me think about this. And he goes home and he finds somebody else. So optimized portfolios contain weird positions. And this is the last fact, which I think is a general fact about portfolios and financial markets, which is one of the things I see in finance, which is my topic, is people are constantly running away from historical data. Historical data is terrible data. Okay? So we're about to go to the study of options. What do people do in options? Right? You have the Black-Scholes model. The Black-Scholes model depends on the standard deviation of the asset's return. What's the first thing people do once they understand how the Black-Scholes model works? Huh? No, arbitrage is something else. Yeah. They go to the market and they say, well, instead of computing the historical standard deviation, let me compute the implied standard deviation, which is what does the market think if Black-Scholes is true? Okay? So people are trying to get away from historical data. All right? So I see sort of a lot of the financial stuff that we do is an effort to get away from financial data. In last week's homework assignment, I gave you some paper suggestions. I don't know if anybody looked at the first paper. The first paper says, can I do better by optimizing using implied volatilities instead of using historical volatilities? Anybody look at that paper? Yeah, what's the answer?
That you can outperform volatility-wise.
You outperform, meaning it's probably better to use the implied rather than to use the, yes. The problem is that financial markets have implied standard deviations, but they don't have implied covariances. Okay? You want to write a great doctorate? I've thought about this. I don't have a solution for this. Here's a good doctoral dissertation, which is, can you find market data from which you have implied covariances, not the actual covariances, that's easy, but the implied. If you can solve that problem, then you're going to make a big contribution to investment theory. Okay, skip that. All right, so what about Black and Litterman? So what did they do? So here's the way I like to think about Black and Litterman. I'll go through this slide in just a second, but I like to think about an investor. Let's say it's a pension fund. So you're a pension fund. And you walk into some kind of office. How do pension funds work? You have a couple of $100 million or a couple of billion dollars or shekels worth of assets, and you farm them out to investment managers. That's very, very typical. Okay? And so you're a pension fund manager, and you go to some kind of an investment manager, and you say to him or to her, you say, invest $100 million for me. Okay. What's the first question? I mean, after you drink coffee and smile and stuff, what's the first question the investment manager typically asks?
How much do you pay?
No. The payment is... What?
Why should I invest in yours?
No. Well, the first question the investment manager should ask is something about risk. Okay? And typically the way this is phrased is, what's your target? No, you tell me your target is, Israeli government index bonds, short-term index bonds. I'll tell you what I advise you to do. You tell me your target is the S&P 500. I'll give you a different answer. Okay? So once you have this $100 million at stake, the first thing the investment manager should ask is, what target do you want us to beat, to match? Oh, okay. So the way I think about Black-Litterman is I think about this particular situation, and then I think, what kind of advice should the investment manager give? Okay? And if the investment manager is honest, what he should do is he should say, you know what, if this is your target, if the S&P 500 is your target, here's my advice. Invest in an index fund. It's cheaper. It tracks the index. You don't have to worry about it. When you go back to your investment committee at the end of the month, you're completely covered. You say, our investment went down because the S&P 500 went down. If it goes up, you can say, you know what, it went up because the S&P 500 went up. It's not very original. Okay? So and by the way, that's very common advice. Here's the Black-Litterman addition to that. The Black-Litterman addition, write it in a different color. Oh, that's also blue. So Black-Litterman, what they add to this scenario is they add the ability to say the current market expected returns are, and then they can give you a little list. Okay? So the investment manager in this Black-Litterman story, somebody walks in with $100 million. They say, our target is the S&P 500. The investment manager says, you know what? Here's what the market is thinking right now. Here are the expected returns. If you agree with those expected returns, here's what you should do. You should invest in an index fund. If you don't agree with those expected returns, tell us what you think, and we'll tell you how to invest. Okay? So that's what this slide says in somewhat drier terminology. And that's what we're going to try to explain in today's class. Okay? So Black-Litterman say, let the investor choose a benchmark. And then you tell the investor, you assume that the benchmark is efficient with respect to its own components. Okay? Remember my first stylized fact? My first stylized fact said that most benchmarks are inefficient with respect to their own components. Okay? So somebody says the S&P 500, you say, you know what? I think the S&P 500 is here. Its S&P is ex ante efficient. Ex post, it's going to be inefficient. But ex ante efficient means you can't outperform. If you don't know anything, you can't outperform the S&P looking forward. Okay? And then this second fact goes on and it says, let's derive the returns which actually make the S&P sit on its own frontier. I'll tell you those returns. That's the Black-Litterman, the start of Black-Litterman. Okay? And then they call this the normal returns. And then Black-Litterman say, well, if you don't believe that, then we'll show you how to implement your views, your beliefs into an optimization process. Okay, so I'm going to take an example. I'm going to switch to Excel now. I have to find my example here. Okay, so here's an example. I have a variance-covariance matrix. I have a benchmark. Now, in the previous examples that I gave, where the benchmark is now, this was always the vector of expected returns. I don't have expected returns now. I just have a benchmark. Okay? And the first thing I'm going to do is I'm going to tell you what does it mean for this benchmark to be optimal given this variance-covariance matrix. Okay? This method, by the way, it's a kind of reverse engineering of the whole portfolio process. In the portfolio process, you take returns and covariances and you find an optimal portfolio. In this process, you take an optimal portfolio, the benchmark, and you find the returns that actually make it optimal. All right? So what do I know? What I know is the benchmark, if the benchmark is optimal, or frontier, then it solves this equation that we've been talking about for 2 weeks. It solves this equation. The benchmark proportions equal S inverse expected returns minus C divided by lambda. Okay, so now you have to solve that equation. All right, so what do? You multiply by lambda. So you get lambda xb equals S inverse expected returns minus C. I apologize to the people over here who probably can't see through my back. And then you multiply, you have to get rid of this S inverse. So you multiply both sides by S, so you get S times lambda xb equals the expected returns minus C. And then you add C to both sides of the equation, and you take out the lambda. You move it over a little bit. I'll write this on the top of the board. And here's the solution. Lambda times S times XB plus C equals the expected benchmark returns. Okay? Let me, and sorry, I forgot to add one thing. C is sort of a general constant, okay? Instead of C, let me write the risk-free rate. So I'm actually going to solve here's the risk-free rate, here's the benchmark. I'm going to tell you which expected returns, given the risk-free rate, put the benchmark right on the frontier. All right? Very simple. It's actually simpler than optimizing, yes.
The Bar is calculated by the historical data.
Oh, I don't know. I made it up.
No, I mean, if you want to practice the model, you'll have to take Bar derived from historical data.
Oh, not necessarily. This is not a bad question, by the way. The question is, where did I get this variance-covariance matrix? And the answer is, either I used historical data, or maybe, as I did in the previous homework, I used some kind of shrinkage technique, which is sort of a combination of historical data and God knows what. Or maybe what I did is I completely made it up, like these guys in the paper. You know, I took the implied variances from the option model and I used a constant correlation. That's also a possibility. It's some kind of a variance-covariance matrix. You can decide. Okay? So here's what I'm going to do. First of all, I'm going to tell you what is the risk-free rate. Now, in our homework, the example was monthly data, but now I'm going to go back and everything is going to be annual now, just to make things simpler. So let's say that the risk-free rate is 2%. And then the next question is, I need this lambda. I have a lot to say about lambda. So lambda, for the moment, I'm going to assume that lambda is 1. I'll change it in a few minutes. Okay? So lambda is 1. I know the risk-free rate. I know the benchmark proportions, because there is the benchmark. Okay? All I need to do is write out this equation. So I'll write it over here. I'll call this benchmark expected returns. So it's an array function. I say lambda times matrix multiply. Now, the matrix multiply, I have to multiply the variance covariance times the proportion. So here's the variance covariance times the proportions. And then I have to add the risk-free rate. And the risk-free rate is 2%. And then I go Control-Shift-Enter. And I make this into percentages. And I do something like this. And I use get formula to show you this formula. Okay, so here's the story. Given a risk-free rate of 2%, given a lambda of 1, and we're not quite sure what lambda means, but given a lambda of 1, given the variance-covariance matrix, given the benchmark proportions, the expected returns that put the benchmark on the frontier are these returns. All right, let's check that. Before we do anything else, let's check. So here's what I'm going to do. I'm going to check. Given the risk-free rate, given the benchmark proportions, given the expected returns, is the benchmark optimal? That's not a big deal. Optimal benchmark is you have to solve the other equation. This is the Black-Litterman equation. the optimality equation is x equals S inverse expected returns minus the risk-free divided by the sum of the numerator. That's what we did all week long. So you say asset 1 okay, so you say matrix multiply matrix inverse variance covariance. Let's see, expected returns minus the risk-free rate. That's the numerator. Now you have to divide by the sum of the numerator. Oh dear, what did I just do? Try it again. Matrix multiplier, matrix inverse, please. Expected returns minus the risk-free rate divided by the sum Control Shift Enter. Okay, so you see this? This is exactly the benchmark. So I start with the benchmark and the covariance matrix and the risk-free rate and some lambda, and I solve for the expected returns, and if those are the expected returns, then the benchmark is indeed optimal. Not only that, it works for every single lambda. If lambda is 2, it also works. If lambda is 0.86, right? Lambda influences the expected returns, but given those expected returns, you always get the benchmark back. Okay? So this is the reverse engineering part of Black-Litterman. All right? There's some other stuff that's true about Black-Litterman too. All right? Remember our homework. We had these two stocks, Citicorp and YRCW, both of which were historical disasters. Okay? What's the most simple thing you can say about expected returns? It's actually, what is a stylized fact about expected returns? Now that you know what? Okay. I think maybe two things. One is, so stylized facts. Well, the first thing is you would expect the expected return of most assets to be positive. Right. By the way, it's a stylized fact because when you took the investments course, somebody showed you some crazy example of a stock with a very negative beta. And then they said, well, to buy this negative beta, you would be willing to expect a negative return. Okay? That's what the difference is between a style. Of course, go find a stock like that. When I used to teach that course, I would always give the example of a law firm that specializes in bankruptcies. I looked for that law firm once on the New York Stock Exchange and I couldn't find it. Okay, sometimes people say gold. It's hard to find negative beta stocks. Okay, so one stylized fact is the expected return should be greater than 0. There's actually another stylized fact, which is that the expected return should be greater than the risk-free rate. Okay. Notice that by construction, the Black-Litterman expected returns, they're all bigger than the risk-free rate. Okay, so it sort of makes sense. It follows what you think should be the format of these things. Okay, well, I think it's 8 o'clock, so let's take a 15-minute break, and we'll come back and I'll tell you about Lambda. Okay. So I explained the basis of this this Black-Litterman model. Now I want to talk a little bit about about Lambda. Okay. By the way, I should say that my explanation of I try in this class to do nothing that's terribly original, but my explanation of Black-Litterman is really very, very different from most explanations, and that's because when I started to work on this, I read all the papers in this area, and I couldn't understand a damn thing. And I think this is more or less true. This is what they really meant to do. And that extends to the way I present this with Lambda. If you look at most of the papers in this area, they use some other symbols, and they go into all this stuff about market risk aversions. I can't understand. Okay, so let me give you my take on Lambda. Okay? This is the optimality equation. This is what happens when you take the optimality equation and you turn it around to solve for expected returns. Okay? Now, what's the fact, and this you can see in Excel, what's the fact about this equation? The fact about this equation is that Lambda is not determined. Any Lambda works. Okay? So you have to figure out what Lambda is. All right? Now, yes?
Why isn't it the sum of the numerator?
It's a sum of the numerator, but if you say Lambda equals 0.86, then you get that these returns optimize for the benchmark. And if you say Lambda equals 0.3, you get the same result. So what's Lambda?
But why isn't it necessarily must be the sum of the numerator?
It's always the sum of the numerator. Whatever you put as Lambda is going to be the sum of the numerator. That's the problem. That's just mathematics. Okay? So mathematically, this works. That's what I showed you. Okay? But economically, what's Lambda? All right, so here's my take on Lambda. You need an extra assumption. To determine Lambda. Okay, now let me give you some extra assumptions that I don't know about work, but extra assumptions that give you answers that I think make sense. Here's what I think is the most reasonable, plausible extra assumption. The most reasonable extra assumption is the expected benchmark return is some number. 8%. I just made that up. Okay, don't ask me. Okay, so the client walks into the investment office. He says, if you give me the right answers, I'll give you $100 million to play with. My target is this benchmark. And the investment manager says, well, if you don't give me anything else, then I'm just going to tell you that the benchmark is ex ante efficient, and I'm going to tell you what that means. But I do need one thing from you. What do you think is the expected benchmark return? Okay? Or maybe the investment officer says, you know what? We've done a lot of research on this question. We asked Professor Benninga. No one has ever asked me this question, so I give it to you for free. Okay? And he said 8.5%. Okay, so this is Simon's expectation, forecast. Okay, now in fact, okay, let's take the in fact. So how do you do the in fact? Well, the in fact you do by taking the benchmark proportions and multiplying them times the returns. Okay, so that's just a simple sum product. So you take this and you multiply it times I guess I screwed up. Okay, so here's what we're going to do. We're going to change lambda so that this forecast is true. That's not a big deal. In fact, if you look at the slides for this particular chapter, or in the chapter, I give you the answer. There's actually an analytical answer to this. But let's just play with this for a second, okay? So if lambda, so I'm playing with this cell, and I'm looking at this cell, and I'm trying to make this cell equal to this cell. Okay, so if lambda is 0.3, the expected benchmark return is 5%. If lambda is 1, it's 11%, so somewhere between that, 0.8, 0.6. Okay, you can even, we'll drop all of this and we'll say data, goal seek, set this cell equal to 8.5% by changing lambda. Okay, so can I help with this?
How did you get here?
How did I get here? I took my car from Jerusalem this morning. What? Sorry, wasn't that funny? What?
What is the last function? Goal seek.
I just used goal seek. Or you can use solver. Solver is better because the next time you do this, you can remember. But in fact, there's a solution to this, and I'm going to give you a homework problem on this, and I'll make you find the solution. Okay? But you get the point. This portfolio, I found my return so that this portfolio is optimal because I have this belief that ex ante, whatever the benchmark is, it's optimal. But it turns out that doesn't completely answer the question. You need another fact, or you need another assumption, and this is an assumption. Okay, maybe you can get this from market data. That's a different book and a different thing. I think you can actually get this from market data, but never mind. That's something else. All right. So if you look at yes.
How do you know there's only one solution?
What?
There is only one solution?
You know what? That's a great mathematical question. Did you get that question? The answer is, how do I know there is only one solution? Well, let's be a little more specific. How do I know that for a given lambda, there is only one solution? Right? Because every lambda gives a solution. And the answer is, how many times do you think we draw this picture in an average investment course? The answer is, that's it. There's only one solution. It requires a little more. Listen, this is not a course in mathematics. The answer is because the feasible set is concave, and because when you maximize over a feasible set from a constant, then there is only one point of tangency. That's the answer. Okay? But that's not a bad question. Okay, so I don't know. Maybe I'll stop here, okay? I don't want to overload you with stuff because I want to be able to give you a homework assignment which then drives home this point. There's another point here. Let me just tell you the one other point that's left with Black-Litterman. So you walk in, the investment advisor says, you know what, I studied financial engineering, I studied Black-Litterman, I think that 8.5% is the expected return. I think these are the asset returns. All right. Now, there is something you could say about this, and what you could say about this is you could say, you know what, this is what the market expects, but in fact, I've studied asset 1. And I think the asset 1 expected return is 10% and not 9.61%. Okay? So there is a slight addition to this little game. All right? And the slight addition, not addition. The slight addition is maybe you have an opinion, or Black-Litterman called these things views. Maybe you know something. My cousin's girlfriend's brother, actually, it's her brother-in-law and they got divorced, but never mind, works for Citicorp and he says things are better than the financial statements. I think the returns are going to be better. So this is not 9%, it's actually 10%. So now you have a point, okay? So I'll just show you this over here and not... Okay, so what I'm going to show you now is not totally true. I have to work on this a little bit next week, but I just want to make the point of how this might actually lead to a theory of active portfolio management. So far, this is not a theory of active portfolio management. This is a theory of completely passive portfolio management, which just tells you what you must be thinking if you're buying this index fund. Okay, so here is my Simon's opinions on returns. Okay, I agree that asset 2 has 6.2%, and I agree that asset 3 has 10.23%, and I agree that asset 4 has 2.91%. But I think, because of this family relationship that I have, that asset 1 has a 10% return. So, what's Simon's optimal portfolio? Okay, well, we know how to do optimal portfolios. You take that, I mean, how many times do I have to say this? You take S inverse times the expected return, blah, 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 blah. So here, I'll show you. It's M mult, M inverse, times my expected returns. That's the difference now. If I did this with I don't have to say any of this, minus the risk-free rate. It's the same risk-free rate. Presumably, I don't have any opinions about the risk-free rate, right? I'm smart, but I'm not that smart. Divided by the sum Okay, now let's just, before I do anything, let me just check to make sure that I did my mathematics right. Okay, so if this is 9.61%, okay. All right, did you get this? So I get back this I'm not supposed to point at that board. This is the portfolio that I start off with, okay? So here's what happens. You walk in with your 100 million or your $100, and the investment advisor says, you know what, the risk-free rate is 2%. We think that the market return is going to be 8 whatever, and we think these are the expected returns. And then you look and you say, you know what, this is what I think. Here's my optimal portfolio. Okay? Let me tell you why this is a big improvement on what we learned previously. All right? If anybody here ever sat on an investment committee? Okay, so here's what happens on the investment committees that I've sat on. Somebody comes in and they say, we think this, we think that. Nachon, is that what happened in your investment committee? And then after about 2 hours, when everybody is exhausted, because you have to talk for at least 2 hours to make sure that the records, the minutes of the meeting reflect that you thought deeply about this, because otherwise somebody's going to sue you. After about 2 hours, you say, okay, we've heard all of these opinions. Here's what we're going to do. All right? And then you make up some bullshit investment policy. Okay? So here's the Black-Scholes take on an investment committee. You come in, and people say, this is the opinion. And you say, no, I don't agree. This is my opinion. And you get a different portfolio, but the basis for this different portfolio is the existing benchmark. Okay? So here's another thing. I've been in investment committee. Somebody says, Bank Hapoalim is better than discount bank. Okay, so then you say, do you think that that means when we invest in the Tel Aviv 25 index, we should completely eliminate the discount bank from our portfolio? And they say, are you out of your mind? Okay, because what's going to happen? What if we're wrong? Okay, so you say, okay, so what do? You say, well, let's make a slight adjustment. We'll take a little more of Bank Hapoalim, we'll take a little less of discount bank. So then you say to them, what about IBM or whatever? And they say, I don't know, let's keep that the same. Okay, but this procedure allows you to start with some market opinions, allows you to change your own opinion, and allows you to build off of that and make adjustments. All right, that's pretty cool. That's actually sort of a neat way to do things. Okay, I have more to say about that next week, and the reason is that what I just showed you is wrong. And it's wrong. Does anybody know why it's wrong? Did I tell you this is the one joke I can tell on television. Okay, this is my favorite ethnic joke. Okay, now I know you're not supposed to tell ethnic jokes, so I will tell you that this is I call this a generic ethnic, are you looking? A generic ethnic joke. So the way to tell an ethnic joke of the kind that I want to tell you is you have to make up an ethnic group that is not watching this video. I have a group, okay? It's the Falkland Islands, all right? The Falkland Islands, there are 1,200 people and 90 million sheep in the Falkland Islands. There's no university. Not that they're dumb, but okay. So here's the joke. There's an Israeli version to this joke, which I can't tell. The joke is, why do Falkland Islanders have narrow shoulders and tall foreheads? The answer is because when you ask them a question, they say, I don't know. And then when you give them the answer, they say, I knew this all the time. Okay, now I have to say, I've never been to Falkland Islands. I don't even mean this about the Falkland Islands. It's just a generic joke. Okay, so I've gotten out of this. So what I showed you, why is that wrong? And the answer is because it turns out that if you have an opinion about asset 1, you must also have an opinion about assets 2, 3, and 4. And the reason is that there's covariance. I knew that all the time. Okay? So it's not quite as simple as it looks. All right? There's assets. Asset returns co-vary. So if you think that the first asset is going to do better, apparently that means that the other assets are also going to do different. Maybe not better. So I have to make that adjustment. I'll show you how to do that next week. Okay. So that's enough for today. Let me save this as in case anybody wants this. What?
What exactly is Lambda?
Lambda is, the question is, what is Lambda? The answer is, Lambda is something that's related to an external fact that you have to specify. Actually, that's not such a bad question. In this case, Lambda influences the expected return on the benchmark. But by the same token, you could say, I think the expected return on asset 1 is 12%. That also determines Lambda. Okay? You just need one extra fact. Somebody has to give you a fact that says something about market conditions. Yes, I'll give you some.
Lambda is like a factor that helps you to get to an expected return?
A specific expected return, yes. Did you have a question? No, okay. I just want to save this. Okay. Okay, now, the rest of this class, I don't have so much time, I have about 50 minutes. The rest of this class is a review of what I think you should know about options. And everything I'm saying is in chapters 13 and 16. So, and I'm going to ask you some homework questions about this. And the homework questions will be from the book. Do this exercise, do that exercise. And it's easy to cheat on that part of the homework because the book has a disk, and the disk has all the answers to all the homework questions. So I will be disappointed if you cheat, but I will also be disappointed if you get less than 100% on those particular questions. That's sort of a problem. Okay. Let me tell you how I teach options. Not in this course, but when I teach an options course. So when I teach an options course, what I do is I give a bunch of definitions and examples. What's a call, what's a put, that kind of stuff. What's American, what's European, okay? And then I spend some time making drawings. This and that and, all that stuff. Actually, that's not an option drawing, but you get the idea. And then we do some what we call arbitrage propositions. And that's all very standard. Actually, the easiest course in the finance curriculum to teach is an options course. All right? And the reason is, if I get a new lecturer in my department and I want him to teach an options course, I say to him, take a book. Any good options book will do, let's say Hull, and just teach chapters 1, 2, 3, 4. Teach a chapter a week until you get to the end of the semester. It always works. Okay? It's a good book, too. So you take the definitions, the examples, the drawings, the arbitrage propositions. Now, in most options courses, the next thing they do is the binomial model. And then they do Black and Scholes. Okay? I reverse the order. Okay, the way people teach options is they say, well, you have the binomial model, and if you do this, that, and the other, then it converges to Black-Scholes, and by this time no one is listening. So what I always do is I say, listen, I'll show you the Black-Scholes propositions, I'll show you the Excel spreadsheets, I'll explain to you how this works, and then I'll talk to you maybe, if I have time, about the binomial. Okay? And in fact, what I'm going to do in this course is exactly that, and this is only the start. This is sort of the starting point. I'm going to do a full binomial sort of explanation, and then I'm going to take this binomial and I'm going to do Monte Carlo. In between this binomial and the Monte Carlo, I also have to explain to you something about log normality. Okay, so today I'm just doing the top part. All right, so very quickly. Okay, everybody knows this slide, right? What's an option? It's either the right to buy or to sell a stock or something else at a given future price. What's the difference between a European and an American option? The answer is that a European option can only be exercised on a specific date, and an American option can be exercised on or before a specific date. A slightly more difficult question is, where did this terminology come from? European versus American. The answer has to do with, with the Vietnam War. Okay? Sometime in the 1960s or late 1960s, Paul Samuelson, who was a very, very, very famous economist and an American, wrote an article about options, and he wanted to talk about this difference between exercising on a specific date and exercising before or on the specific date. And it was a time of great political tension and anti-Americanism, so he called the inferior option the European option, and the superior option the American option. This is actually true, and that's where this terminology comes from. It has nothing to do with options. In fact, options were first traded in Amsterdam, as far as I can tell, in the 17th century, and there's a book about this written by a Jewish guy in Ladino, actually, and you know, the options that he describes, they were on tulip bulbs. It turned out to be a very bad long-term investment. Those options are all European, all American options. They can be exercised at any time. Okay. This also is the notation that everybody knows, right? I'm going to use C for a call and P for a put, and either X or K, usually X, for the exercise price, which is also called the strike price. And I'm going to use S for the stock price, and R for the interest rate, and sigma. That's the only interesting thing right now about options is the standard deviation of the stock return. So it's the standard deviation of the return of the stock on which the option is written. Stop me and ask me whatever you want. But, and this you also know, what's the cash flow pattern of an option? Well, if you buy it, it's got an initial negative cash flow. When you exercise it at termination, it has this max ST minus X cash flow. And in between, if it's European, it has a 0. And if it's American, maybe you'll want to exercise it. There's something else on this that you also know on this slide that you also know. If you buy an option, then the payoff is max ST minus X or 0. If you write or sell an option, then the payoff is minus max ST minus X or 0. But of course, the initial cash flows are also reversed. All I think that's what I just said. And here's a put. Okay, this is for calls, and for puts, it's max x minus ST or 0. I hope I'm not saying anything that people don't know. We skip this. This is sort of, how do I give an intuitive explanation of what an option is? Well, an option is sort of I like to think of it as a one-sided bet. It's a bet, if you're talking about a call, that the stock price will go up, but you don't much care if the stock price goes down, in the sense that greater down doesn't affect your return. You lose the same amount of money. Or a put is a bet the stock price will go down. I call those things one-sided bets. Now, I'm going to skip the drawings. I'm also skipping the examples. Okay? And I'm going to go straight into sort of what you might call arbitrage propositions. All right? In order for you to understand where I'm going with the rest of this course, you need to know there are a lot of arbitrage propositions. I once had a student in Jerusalem, a guy named Samer Chajichya, and he wrote a paper on, this was his master's thesis, on every single arbitrage proposition he could find. I think he found about 100 of these things. He went on to do a PhD at MIT, and he's now the director of financial engineering at Fidelity Funds, so not bad. So there are a lot of arbitrage propositions. Okay, I need for this course about 4 or 5. All right, so here's my version of arbitrage propositions. Here's the first one. Arbitrage proposition 0. This is such an idiotic proposition that I refuse to give it a number. Here, I'm skipping all the drawings. Although they're made with Excel, they're very cute, don't you think? Okay, here we go. All right, so arbitrage proposition 0 says that an American, I'm going to do these only for calls, basically. An American call has price C or C0, and the stock that it's written on has price S0, and the exercise price is X, and the proposition says the call price has to be greater than S0 minus X. That's sort of the most, you know what, max S0 minus X, or 0, sorry. That's probably the most simple thing you can say about a call. All right? And, you know, I don't know if you need a proof, but here's a numerical example that shows you the arbitrage. So in this numerical example, I say, well, suppose the call price is 5, and suppose the stock price is 50, and the exercise price is 40. Actually, you know what? Let me erase this for a second. Let me ask you a question. Why should C0 be greater than 0? Why can't it be negative?
Options will be given for free.
What?
Options will be given for free.
Okay, you know, it can't be negative because you're getting something. Not only are you getting something, you're getting something which is, it's always positive or 0. So if you're getting anything significant, the price must be positive. Otherwise, you violate a really, really, really basic arbitrage proposition in finance, which says if you have only positive returns, then you must have to pay for them today. Okay, so now I can go back to do my example. So in my example, this is 5, this is 50, and this is 40. What's wrong with that? The answer is, well, if it's an American option, then you buy the option, exercise it, you make $5, and you get, $5 for nothing. Okay? So the first and most primitive thing you can say about an option is, if these are the facts, this price is wrong, it has to be at least a little more than 10. Let's say 11. Okay? All right. Okay. So here's a non-trivial fact. In fact, this non-trivial fact was invented by Mr. Merton. Okay? This is totally idiotic. This is much more significant. This is the fact that says call is bigger than max S0 minus X or 0. This says that the call price is bigger than max S0 minus the present value of X at 0. Okay, I prove this in the book. The proof is not very difficult. In fact, it's one of these things you can actually do in an options course. It requires no mathematics, just a little bit of logic. I'm not going to do this proof. I would just like to point out maybe two things. One is that, and I forgot something. One is that this is less than this. Okay? Let's set this up in Excel for a second. I'll show you.
Present value is lower.
Present value is lower. Right. So here, let's say I've got S0 is 50 and X is 40, and proposition 1 says the minimum price for C0 is, that's the minimum, is max S0 minus X or 0. Okay, so what is that minimum? Well, it's max S0 minus X or 0. It's 10. It's got to be at least 10. Okay, now, proposition 2, here's the point I'm missing. The call is American. Proposition 2 says you're right. After I talked about, I don't know the difference between 0 and 1, that's fine. Okay. Proposition 1 says for a European call, C0 is bigger than max S0 minus the present value of X or 0. Okay. So right away, I notice that I need an extra factor. I need the interest rate. Okay? This is independent of the interest rate. This requires an interest rate. Okay? So we'll make up a number. R equals 10%. Okay? Now, not only do you need an interest rate, but in order to compute a present value, you also need a time to maturity. I didn't need that either. Okay, so T equals, we're going to do T in years. let's say 1 year. We'll change this in just a second. Okay, so what's the minimum? Well, it's max S0 minus, now, here I have a problem. How do I write the present value if I know the interest rate? Okay, and the answer is it depends on whether you're using continuous compounding or discrete compounding. There's no correct answer to this, and we're going to do both Black-Scholes and we're going to do the binomial model. The binomial model is a discrete model. Black-Scholes is a continuous model. So the actual numerical answer you get for this particular proposition depends on what you're assuming. Okay? So for example, if it's continuous, then the present value of x equals e to the minus rt times x. If it's discrete, the present value equals x divided by 1 plus r to the power t. It just depends. Okay? So let's assume, I don't know, what's your favorite method of compounding? Discrete. You see, I listen to you sometimes. So you say, here's x divided by 1 plus the interest rate to the power t, or 0. I'll find get formula. Okay, so the first thing you notice that this number is much larger than this number. The present value is smaller, but the difference between the current stock price and the present value is larger. Okay, so this proposition gives you a much more severe bound on the present value than the first proposition, on the option price than the first proposition. I don't know, is there anything intelligent left to say about this? I'll just show you that if you do this in continuous time, so you say B1 minus exp minus the interest rate times the time to maturity times the exercise price that's a different price. So that's continuous interest. Okay, what's the next proposition you need for options? What's proposition 2? What? No, not yet. There's one. The next proposition you need is the one that says a European and an American call have the same value. Well, there's a proviso here. What's the proviso? Anybody remember?
You will never exercise
No, the proposition is it's never worthwhile to early exercise an American call. If, thank you very much, if the stock pays no dividends before time t. Okay, and so proposition 2 says early exercise of American calls is suboptimal if no dividends on the underlying stock. You don't need no dividends. All you need is no dividends before time t. Anybody want to offer a proof of this that I can write down in 10 seconds or less? Proof is completely trivial and depends on this. Okay? I tell my ethnic joke again, but I'm not going to, I don't want to get in trouble with any ethnic groups. So the proof goes something like this. You have an option. It expires, it expires at time t. And at time little t, which is before time t, you're thinking about early exercise. You're considering early exercise. Okay, now why would you consider early exercise? There could only be one reason. It must be that st is bigger than x. Right? Because if st is less than x, then why would you early exercise? It's not going to give you anything. Okay? So st is bigger than x. You're thinking about early exercise, but there's still time left on the option. The option still has time value. So the question is, what do you prefer? Do you prefer this is early exercise, and this is sell the option, in which case your minimum return is st minus x divided by 1 plus r, which is the interest rate, to the power t minus t. That's the amount of time left. And this is bigger than this. So the whole proof comes from this previous proposition that says, well, you want to get rid of the option? That's okay. But if you're going to get rid of the option, you should sell it instead of exercising it. Okay? So that's the proof of this proposition. Okay? And then I need one more thing. I need put-call parity. Okay? Let me, instead of writing this down, since here it's called proposition 4. What's proposition 3? You know what? There's a mistake in the slides. This should be proposition 3. Okay? So here's what put-call parity says. Put-call parity says, I hope you know this already, that if you take a put, a call, and a bond, and a stock price, those are 4 things, then 3 of those determine the 4th one. One way to write this is the put plus the stock equals the call plus the present value of the exercise price. That's true, by the way, for European options. It's not true necessarily for American options. But for European options, when there's no dividends on the stock before the exercise price, put-call parity is true. Okay, I'm not going to prove it, although the proof is fairly trivial. So that's those are the four propositions, 0, 1, 2, 3, not that I need for you in order to do options. Questions up to this point? That's all totally trivial, right? Okay. All right, let me close this down. Okay. What's the next thing that I want to talk about? The next thing, this is all this review stuff, right? The next thing I want to talk about is Black-Scholes. Now, what I'm about to do is I'm about to give you a completely mechanistic introduction to Black-Scholes, and when I finish, that's the end of this class. Okay? So I'm not interested in proofs. All I'm interested in is some basic concepts in Excel. All right? So this is all the same stuff we've had before. Oh, sorry, that's also the same slides we had before. Okay. I always joke, and I'll show you this in just a second, that Black-Scholes is what I call a really amazing mathematical theorem. Okay, what does a mathematical theorem look like? It starts with some ifs, and then it has a then. And then a really good mathematical theorem follows the then, that's the conclusion, with a where you're trying to explain all this other stuff you say. So what does the Black-Scholes theorem say? It says if the stock price is log normally distributed, what does that mean? Next week. If the stock has no dividends before expiration, and if the option is European, so those are the three ifs, then you have this formula. Okay? The top line is the call price, and the bottom line is the the next line is the put price, and the where is this this formula that I never remember, you know, D1 and D2. And, all right. And then there's the where. And the where says, well, N is the normal distribution, and sigma is the standard deviation of the stock price returns, and T is the option exercise price. Okay, so it took me 3 slides: the ifs, the then, and the where. Okay, so how do you understand this proposition? Well, the best way to understand it is in Excel, I think. Let me just save this someplace where I... I did it again. I picked the wrong chapter. There we go. Okay, so here's one way to explain Black-Scholes. Black-Scholes depends on 5 factors. It depends on the stock price, the exercise price, the interest rate, the time to maturity, and the standard deviation of the stock price returns, which is sigma. So you have these 5 factors. Then you have to do some calculations. What do you have to compute? You have to compute D1 and D2. And you have to compute ND1 and ND2. And ND1 and ND2 are just values of the standard normal distribution. So the standard normal distribution, this is supposed to go through the y-x-axis. The standard normal distribution is symmetric around the x-axis and the y-axis. And if this is D1, then this is ND1. And Excel has a function that does this computation. It's called norm dist, norm standard distribution, and you put in the value D1 or D2. Okay, so here's norm dist. By the way, just, there's a few things we know about norm dist. So for example, if D1 is 0, what's ND1 going to be? Phew. Yes. Okay. If D1 is 1, .84, that comes up, you know why that comes up? That comes up when people say, listen, what's the area on this curve between +1 and -1? So this is 0.84, okay? And if D1 is -1, then this is 0.15, and the difference between 0.84 and 0.15 is 0.68. It's actually 0.69, 68 point something, okay? And that's this number that always comes up. What happens if it varies 1 standard deviation from the mean? Okay, so I'm not making an advertisement for norm as this, but it actually computes correctly the values of the standard normal distribution. And then, so you've got the data up here. You've got D1 and D2, and ND1 and ND2, and now you can compute the value of the call and the put using the Black-Scholes formula. Now, according to the Black-Scholes formula, the call is S ND1 minus X e to the minus RT ND2. And the put, that's what I computed here, 8.64. And the put is, well, there are 2 ways you can compute the put. One way is to use put-call parity. So put-call parity says, right, we said put-call parity is S0 plus P, or S plus P, equals the call plus the present value of the exercise price. So the put is equal to this. So you could just compute, you take the call from here, you take e to the minus RT times the exercise price, you subtract out S. That's what I did here. There's also a direct formula. Of course, this is, the direct formula and the put call, these are not different formulas. This is the same thing. It's just doing a tiny bit of algebra on the normal distribution. The direct formula is minus s n of minus d1 plus x e to the minus rt n of minus d2. That's what I did here. You know, and then there's this hand waving. It's completely correct, by the way. This hand waving explanation that says, what's a put and what's a call? Well, a call is a long position in the stock. And a borrowing position in the risk-free rate. And a put is a short position in the stock and a long position in the risk-free rate. Okay, all of these things are completely correct. Okay. You've got Excel. You can do all kinds of neat stuff like run data tables. And what do I see in this data table? I varied the stock price, and I computed the call price, and I computed the intrinsic value. Okay? By the way, I always use this data table to explain to people that it proves that also in the case of Black-Scholes, it's not worthwhile to early exercise a call. How do you prove that from here? Yeah, just yell. What?
The call price is always above the
Okay, the call price is always above the intrinsic value. The intrinsic value gives you the early exercise value, but the call price is bigger, so you might as well sell it. Okay? Now, one of the miracles of Excel is I can just change my definitions a little bit and produce the same graph for a put. Okay, so what's a data table? You reference the initial example. Here, I reference the call price. So now I'm going to reference the put price. In the meantime, my graph is a little screwed up. Okay, and then I'm going to change the intrinsic value. The intrinsic value here was max B2 minus B3, but if it's a put, it's B3 minus B2 or 0. Okay, and you know what? I think I've even got this. Isn't that cute? I love Excel. Who asked me why I teach with Excel? It's because it's so cute. Okay, and now, just to make the point that I want to make, instead of looking at a call with 3/4 of a year to maturity, let me take a call with 3 years to maturity. I just want to exaggerate. I'm an exaggerating type of person anyway. Ah, that's what I wanted to show you. Okay, so why doesn't this early exercise proposition work for puts? And the answer is that for puts, you get this area over here where the intrinsic value is more than the Black-Scholes price. So now the Black-Scholes price is a price for a European put. But if you could early exercise, then you would stand to benefit. So an American put is actually worth more. It's worth more here than a European put. Okay, that's sort of cool, right? All Excel proofs. Okay, so that's one thing you can do. All right, here's another thing you can do. You can write Can we see that? Oh, there's a way to make these letters bigger, but I don't have time to do that. So you'll just have to suffer. anyway, there's a theory that says if you don't suffer in a course, then it's probably not worthwhile. What did I do here? I wrote a bunch of VBA functions that price options. Every version of Excel, the first thing I look at is to see if Microsoft has added Black-Scholes to its stable of hundreds of financial functions. So they have, for example, every depreciation function that has ever been mentioned in a finance course. Not just straight line, but double declining balances, stuff that I once knew and have totally forgotten. But they don't have Black-Scholes. I don't know why. So this is all very primitive stuff. I define D1 and D2, and then I define the Black-Scholes call functions, call and put. My put function, by the way, is just straightforward put-call parity. Okay? And then I have a call volatility function that I'll show you in just a second. What's the point? The point is, here's the same example I had before, and this time, instead of doing all these computations, they're all buried inside of VBA, but of course they give the same answers as before. So you could write a VBA function and do that. What else do I want to show you? Really, there's only one other thing I want to show you, which is implied volatility. What's the difference between volatility on a historical basis and implied volatility? Anybody want to tell me? You extract.
The standard deviation from
Right.
when you have both.
Right. So how do you compute volatility? I mean, presumably, when I do an option pricing model, everybody agrees on the price of the stock. Everybody agrees on the exercise price. The interest rate is actually sort of an interesting question, but let's say, interest, by the way, option prices are not very sensitive to interest. Okay? Try this as an experiment. Raise the price of the stock by 10%. So I'm going to put in 55, and you guys look at the call price and the put price. Okay? That's why we have Excel, right? Wow. Stock price goes up by 10%. The call price goes up by 50%. The put price plummets. Okay? You can do all these kinds of experiments. The option is a highly levered security. Okay? What would happen if the interest rate went from 4 to 5%? All right? So I'm going to push enter, and you look and see what happens to 8.64. Okay? It went up by 22 cents. Now, remember, what's the probability that the stock price goes from 50 to 55 in a day? It happens, right? It's not, I mean, it's a sort of a small news item, not much, okay? What would happen if the interest rate went from 4 to 5% in a day? Well, all hell would break loose, right? That would be a major economic event. So the point here is I was saying, I know what S is, I know what X is. Maybe I don't know what R is, but it turns out not to be critical in this computation, okay? Presumably, I know exactly how to compute the time to maturity. The one thing I don't know is how to compute the standard deviation, okay? And for the standard deviation, there are two methods. One is from historical returns. I see my time is almost up, so I'm not going to do this. There's an example in the book. And the second method is the implied. volatility. Now, the implied volatility is, it's simply the sigma that makes Black-Scholes, the Black-Scholes formula match the observed option price. So we can give a very, very simple example. So suppose that the market call price, meaning the price you observe in the market for this particular option, stock is 50, exercise is 45, etc., it's $10. What's the standard deviation? Well, you can play with this a little bit. You know, is it 40%? Almost 39%. I don't know, I'll leave this to you. You know, you can do, it's obvious, right? Okay? My contribution to science is I wrote a function. Except I can't spell the name of this function. I hope it's right. It's called call volatility, and it says put in the stock price, put in the exercise price, put in the time to maturity, put in the time to maturity, put in the interest rate, and put in the target call price, meaning the market price, 10. And that's the implied volatility. What? Is that a comment? Okay. Next week we will explain how this works. Yes?
What to do if you have another problem?
I'll talk to you next week. Okay. See you next week.